Hello, everyone, and welcome to today's SANS webcast, Format String Vulnerabilities, the Impact of a Leaky Program. My name is Carol Auth of SANS, and I will be moderating today's webcast. Today's featured speaker is Michiel Lemmens, SANS instructor candidate. If during the webcast you have any questions for our presenter, please enter them into the questions window at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be available for viewing later today and can be found on the SANS registration page. And with that, I'd like to hand the webcast over to Michiel.
Thank you, Carol, for your introduction, and welcome here today to this webcast on format string vulnerabilities, the impact of a leaky program. As Carol mentioned, my name is Michiel Lemmens. I am a Belgian national based in Brussels currently, but I grew up in the northeast part of Belgium, the nice rural parts of Limburg. It's a very green province, and it's a very nice and quiet place to grow up. But 8 years ago, I changed that to Brussels, where I moved and currently work and are based. My current employer is CERT-EU, which is the cybersecurity provider for the European institutions, bodies, and agencies, which means that they refer to us for their cybersecurity needs. We have the more famous institutions or more known institutions such as the European Parliament, the European Commission, the European Council under our wings, but also the lesser known and smaller institutions that count on us to provide a good security for them. And there's about 80 of them. Many of them have very specific sectors, are active in specific sectors of the business. And well, they revert to us for their cybersecurity needs, incident response team, security consultation, cyber threat intelligence, and also offensive security operations, red team operations, where we test our clients or constituents, as we call them, security to see if they measure up to a attack on their system. And that is the team that I am part of. I also do some solo consulting, and as Carol already mentioned, I'm a candidate instructor for the SEC 660 course currently. So if you're interested in taking that one anytime soon, you may see my name appear on the ticket as well. If you want to contact me through email, you see my email address on there, michiel@michiellemmens.com. You can follow me on Twitter @michiellemmens, where you can find some cybersecurity related information. Sometimes you can find some funny pictures I find lying around somewhere. Or perhaps if you're interested in some Belgian societal issues, you can always refer to that, and you can see me tweeting there as well. As it is on my Twitter and here today, any views you hear today are my own and are not linked to my employer or my clients, of course. Just on a practical note, if you see me looking around, I have a 4-screen setup here. Just to give you an idea, on the right, I am controlling my right, so your left likely, I'm controlling the presentation, so the software for the GoToTraining and GoToMeeting is there. In the middle is the screen I'm speaking from to you, and to my left is the presentation as you see it. So if you see me looking around, it's not because I have more interesting things to do than talk to you today. It's just because I have this setup around me to make sure that I can accommodate this presentation as fully as possible. Now, we're not going to spend too much time on the intro because we have quite a lot of ground to cover. Let's dive into our subject today, format string vulnerabilities. This presentation will be put up in 3 parts. We'll start talking about what format strings are in C and C++. We'll have a look at what they look like, how they are used, for what they are used, and what their syntax is. Then we'll look at exploiting these format strings. And you may have seen in the short recap that we'll be discussing leakage, memory leakage, which is generally the most known feature of format string vulnerabilities, is leaking info from memory. We'll also be looking at privilege escalation vulnerabilities introduced by wrong use of format strings, and also buffer overflow conditions, which are a very interesting class of vulnerabilities because they generally allow further exploitation towards getting control of a program. And finally, of course, protection against this exploitation. I am very much a red teamer in the sense that I love the mindset of no security control should be considered secure unless it has been duly tested, which is basically what a red team exercise does. Let's go over the setup of your network or your systems and see if they are able to resist a certain sense of attack. Well, That's something we'll be looking at here as well with the format string vulnerabilities, but the goal in the end is the same. We want to create safer programs, safer environments. We want to have more safety, more IT security in the networks of our clients. So in the end, any real red teamer is also a real blue teamer. They will be sharing their information so that our clients can be safer. So we'll be discussing the protections against the attacks that we see today as well. Thankfully, they're easy protections to follow. There are a couple of principles there. They're not too difficult. So maybe we'll be able to do away with format string vulnerabilities soon because you'll all be implementing these, of course, 100%. Now, format strings in C, and let me draw up a pen here. Format strings in C are a formatted way of displaying data. That's the most important part of it. We want to display data generally on the screen to the user or to the program in a formatted way. That's the clue where the intelligence comes in, and it's not just displaying data. We want to do it in a formatted way, and there are some specific characters in there, specifier characters, that allow us to say, okay, we want to introduce a string here or an integer or a float. So that's basically the goal of a format string in C and C++. And one of the most commonly used functions for that is printf. This is a simple example with a format string, and this part here is the format string being used, which will be printed out as long as no special specifier is met. When a special specifier is met in there, this placeholder, if you will, this is a placeholder value for what in the end will become the value of the variable that's here. So this will be replaced and put into there. And that will then be printed out to the user. So it's basically a way of showing certain information to the user or to a file or to another variable we'll see later on, and allowing it to be with a specific syntax in mind, with a specific formatting in mind. That's a very, very basic understanding of what it is. I think we're 5 minutes in the presentation. We can talk hours about this, but that's gonna take too much time. For the benefits of this this explanation, this will be sufficient for this webcast to deal with the problems that we'll be identifying. Now, we saw that %s come up earlier here, this one. We saw it in the string. Well, this will allow us to print out whatever the variable is that's included after the format identifier as a string value. Take the text from there and print that out. That may have well also been an integer value, which is indicated with the %d indicator specifier, which will print out whatever value is there as an integer. We have %s for a float, %x for a hex, and we'll see that one today a couple of times, as well as %p, because it'll allow us to print out pointers in memory towards the user screen. But it's all just a matter of, this category here is all about displaying information. This is not going to be affecting the variables that are included after the format specifier, where the %n will do that. This is going to write towards the variable that's included. And what is it going to write? The number of characters that was printed so far. This is a bit abstract. We'll see it in a second in a demonstration. You'll see what this exactly means. It'll be much more clear if it's not clear just yet. But this will write to memory, and that already should ring a bell when we talk about security, because writing to memory may well be something very dangerous indeed if it allows us to use if it's allowed to be done in a specific way. Now, we saw in the previous slide that we had a sort of a double quoted string here that was used for that format string in there. We can also have a variable in there. You can include a different variable in there and say the variable will be something that comes out of the program as a variable. The variables you include afterwards can also be double quoted strings. You're quite liberal in how you use the syntax there. You can even just print one single line of text or simple line of text without any of the specifiers in there, like this. Although this variable one will still be considered as a format string, so it'll still go looking for the % signs in there to see if there's anything that needs to be format printed out. So that's going to be interesting in a second as well. We'll have a demo in a second coming up, so you'll see what that exactly would mean. There's a whole family of printf functions out there that have different uses. The single one, the simple one we saw earlier, printf, a format string with an optional variable or multiple variables after it. fprintf will also take a format string, but will write all the information to a file stream. If you want to save on disk, you can use fprintf to write to a file stream. sprintf will have the same effect, but write to a buffer, a character array buffer that you identify and that you indicate in here as the first variable, write to this buffer. vprintf will be like the standard printf, but it'll take in the variables as a structure rather than taking them in one by one after the other. You can have a format string printing with vprintf that'll print out information from a structure. And as nprintf will be the same as sprintf, but with bounds checking. We'll see during the mitigations why this one is such an important one. Now, demo time. Let's pull up some demo with all that theory. My throat is becoming dry. Let's pull up some demo here. And you should see my Ubuntu now on your screen. I think this should be large enough to be legible. Let me close the screens we don't need. Cancel. Let's do a clean exit out of this. There we are. So let's look at this first program, and it's quite long, but it's actually a relatively simple program. What it'll do, and I'll spin up the output just next to it, new window, make it a bit bigger, print out the output, and I'll put it next to it here. Let's make a comparison between the two. We say the first line has variable 1 has an int value of 1. This should be legible on your screen. I can perhaps shrink this one a bit. That's too small. There we are. That should be great. Now, what we see in the first line here, the first block, short block of code we created here, we define a int value of 1 and assign it the value of 1. Variable 1 has an int value of %d. This is the format string. The %d will be replaced by the value of 1, and that will be then displayed to the user. That's the use of format string printing in the most simple form. We can do the same with a float. We have a 2 here, 1.3, and print it out in the same way. And you see a bit more addition here. This is just a bit exotic use, or exotic is perhaps much said because people who are fluent in this, and I'm not a C programmer, I'm not fluent in C programming. People who are fluent in this will use this very often this way, will indicate that the total printed string will have a length of 7, including the decimal, and we will have 2 characters after the decimal point. So we see that represented here, 7 characters including decimal points and 2 after the decimal. Now, if we have strings here, we have a character defined as 3, character array as 3, character array yes as 3, and we can print it out the same way with the %s. So that's a relatively simple way to print out strings. Other way to print it out, just printf 3. And what we see happen here is that the first printf has printed out to the screen here. That's the string there. By default, it will not be new line terminated, which means that the next thing printed will be put just behind it. Hello, Michiel is put right behind it. Now, we can also print out the pointer to that variable by using the %p identifier and then putting the ampersand here in front of the 3 so we get the pointer. And we see that the output is the pointer that is to that value, BFFFF0C4. If we want to print out multiple variables, because format string printing is not limited to just one variable, you can just include them one after the other, and then the identifiers, the specifiers will be interpreted in logical order one after the other. Now, one of the more intriguing ones is the writing one. Let's have a look at what this does here. We declare an integer of length 0. Our string will say how many characters will this sentence be, and then we have the %n identifier. What this will do is when it sees the %n, it will take the number of bytes that the current command of printf, the current call of printf has printed, will take that and write that to the variable that you indicate after it. So this piece of text here, up until here, and we can easily check that. It says it's 43 here on the output. Well, let's check it. Let's echo -ne to remove the new line character and introduce it into WC. Sorry, that's the wrong one. I need to take this one. That's the correct one. Of course. Whoops, not HTML, just whoops, and I don't want to enter there. Echo -ne, double quotes, introduce it there, and pipe it into character count. We see 43, so that explains where the 43 comes from. It'll just look at how many characters were written up until now using this call of printf. This is important. We'll see that in a second when we start doing writing to memory with the exploitation. And we can print a pointer to it again. This is not the most exotic one. We already had that one. Print a pointer to it again, which will be, in this case, BFFF F0B8. That's a basic, simple use of format strings, and we are no longer not yet talking about vulnerabilities. This is just how format strings are working and supposed to work. Now, of course, you're here today to talk about format string vulnerabilities, leaking out information and all that. So I'm not going to withhold you from that. Where is that coming from? How would that work? Well, this is a simple program, and we'll see it in a demo in a second as well. But I like to go through this line by line so I can explain what's happening here. This is important to see where things go wrong. We print out a simple line which has no identifiers in there and no variables. That's perfectly fine. We ask, what is your name? fgets will get the input from the user that's currently on the screen. It'll not display a prompt, but rather wait for user input, write the output to the name variable with the length of name and take it from standard in. That's very simple. Printf hello. It does not have a new line, which means that it's going to stay on the same line for the next printf, which is print out the user input. It's a very simple usage of taking input from user and printing it out. Of course, if you take real world programs, oftentimes in between these two here, you'll have quite some functionality going on. You'll have perhaps changing things, adding things, removing things, whatever, and then you'll print it out to the user again eventually. Well, this may lead, and if we look at the next slide, we see the right column changing here. What if a user starts inputting all sorts of format string specifiers in there? Let me put that in a quick notepad so I can show you how this will work then. Let's duplicate what's happening here in this input, and I'll just take it onto the left-hand side so we can see the input on the right that the user has given. So we'll be having printf name. That's what's going to happen, right? That's what's basically being done. Name equals Michiel, %p, 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 and I'll double quote it to make sure we're a bit coherent with C syntax. It's sort of pseudo C that you see me writing, which is, I think, a contradictio in terminus, but this is what's going to happen. Well, what's going to happen here is printf is going to be taking in this copy and replacing name, paste, with that. Now, if there are 3 %p's here, what the program is expecting is to be there var1, var2, var3 after it. That's what the program's expecting because you have 3 format specifiers. Well, as we see in the original code, it's not there. It's just printf name. So what's it going to do then? It's going to print out 0x14, B7FP45C0, 4005D9. What is all that? Where is that coming from? Well, let's pull this up in a short demo and find out where it's coming from. Clear the screen. Do not save. Clear the screen. Nano first format.c. You'll see that this is a simple program that does exactly what we saw on the slide. We declare a variable. We ask the user to input any information to us on the screen. Printf a hello first, and then printf the name. And just for beautification purposes, there's a printf \n there to get a new line after it, so my prompt does not get glued up to the output there. Let's have a look what happens if we run this program. It's called first format. My name is Michiel. Hello, Michiel. It's sort of a hello world program, if you will, except that I am not world, of course, thankfully. Well, let's duplicate what we saw on the slides. %p, %p, %p. We see that we get comparable values being printed out. Now, question is, what is happening here? Well, we'll dive into GDB in a second. One cool feature of format strings is that you can have direct parameter access, which means that I can address this second parameter, for example, that we see printed out. I can address that directly without needing to input a %p before it first. Let me show you how that works. Michiel, $2p. The $2 will tell the printf function to take the second variable that's to be expected, which we see printed out here. We can access the second one. Now, this is going to come in handy very soon when we start selectively dumping out memory, things that are interesting to us. We'll see that working in GDB now. We see there's an ask user function in which we need to be in order to see this working. And we'll be looking at the second call to printf after fgets. So we have fgets, printf, and then the second printf is going to be the one that's the vulnerable one. That's the user input being printed out. Is ask user. Let's have a look. We see the fgets here at the bottom, and my screen is just too small to accommodate fully for it. So let's do this again. This as ask user, a bit more clear. We have an fgets, we have a printf, and then we have this printf, which is likely responsible for what's going wrong here in this program. Let's put a breakpoint there. Breakpoint at ask user plus 98. It's a call, so it's going to be 5 bytes wide. So we need to put on at 103.2 to be just after it to see what happens right before the printf call and right after the printf call. Let's run the program. Michiel, %p, %p, %p. We hit the breakpoint. We're before the printf, where we actually print out values from memory. And let's show some things that are currently on the stack. No coincidence, of course, because I think that's where we're going to find the fun part that we're printing out. This is what's currently the next 4 values on the stack. It's this address, this address, this address, and this address. Well, it's not all addresses. This is likely a length of 20, which is linked to the name. Let's see what happens if we now print out that information that we inputted. We get 14, 14. B7FB 45C0, B7FB 45C0, 400609, 400609. So this is logical. Printf is printing off from the stack, which is where the variables were supposed to be located, printing off information from that. Now, this is an interesting feature. We can print out stack data here. That's quite an important thing we can do. Now, we see that this is the first one we get in our output. Let's look what's at this one here, at that address. What exactly is living there? 0xBFFFF068. Okay, let's look at that as a string. We see it's the string we inputted, so that's being passed to the printf function, the string that we've inputted, and then, well, whatever's coming after that, because there are 3 %p signs, the printf function is assuming it needs to print out this and that, which is why we get this output. This is the bare functioning of format string vulnerabilities in its most simple form. Now, the question is, what can an attacker do with that? Let's have a look what else is on the stack. And for those of you who have some experience with debugging and or exploit writing, by the way, we're going to print double words from the stack because we know one bytes in and of itself. We see that we have the values we already know. And further down the stack, we see a couple of things that are interesting here. These 2 things. Let's have a look at the backtrace here. This is the chain of function calls that is being displayed here in GCC. And we see that our return to main is this address that we find here on the stack. Now, if you've ever taken an exploit writing course, you'll know that buffer overflows will occur by overwriting return pointers that are stored on the stack. Because in the end, when the ask user function is done, control will be passed to this address, which is exactly what we find here in memory. This is the return pointer that's being stored there. The backtrack command is pulling that off the stack here. So this is perhaps an interesting value. The first one that's more interesting, though, is this. This is a program that's compiled in GCC. It's the latest version of GCC. It's compiled without any special operands or special variables. It's just GCC-O format, first format, and then first format.c. Simple compilation, which by default will introduce stack canaries, which will protect these important values here from being overwritten. Now, it would be cool if we could print out this stack canary here. And with the parameter access we saw earlier, the direct parameter access, we'll be able to do that. Allow me to close the window for a second because the sirens are killing us. Brussels is a big city, so siren noises are quite often here. There we are. So we know that this is the first one. This is the $1, $2, $3. Well, 4, 5, 6, 7. Then this is going to be 11 plus 4. So this is going to be 11. This is going to be 14, and this is going to be 15. Let's print that out. Let's print out these 3 values here and see if we can confirm that it's actually those. So %11 $P percentage $14p, percentage $15p. I see I have a couple of typos here. This is $p, yeah, percentage $15p. Let's look at those values on the stack right now, because the canary will be, every time you run a program, the stack canary will be changed. It'll generate a new one. So let's look at the one that we should be finding here. We should be having 2F-B1-2200, 00 being the null terminator. If you're not familiar with stack canaries, I had a talk on this in December. It's on the SANS webcast website. It's recorded, so do feel free to go back to it. I'll explain how these can be bypassed, circumvented, and how they're interesting to exploit writers. So do feel free to refer back to it to see it. And you'll also see me explain this technique, although I don't show it there. We don't demonstrate it due to time constraints. But we see that this is the value we should be finding. And we have these two values we should be finding as well with our output. Let's continue the program and see if we do. Well, 2F-B1-2200, 2F-B1-2200, BFFFF098, which is also there. 4006AB, 4006AB. So we're printing out some sensitive values here from the stack. And we can, by the way, confirm this cookie is in fact a security cookie. If we just look at the beginning of the ask user function, we see that GS offset 14 will hold the cookie value. It's moved into AX and then into EBP minus C. Well, $EBP minus 0xC. We'll see we find the same value, 2FB12200. So we're basically leaking out the cookie. We've just confirmed that we're leaking out the cookie. Now, if this security cookie is generated every time the program is ran, how is it a problem that you can leak it out? It's going to be a new one the next time you run it. If I run it twice, it's going to be another cookie. Well, let's have a look at that, shall we? Proc2 loop. And as the program suggests, it's going to be something that runs in loop. It's a simple program. It doesn't do very much. And I'll, by the way, minimize this for a second just to take out the clobber from the screen. Tell me your name, Michiel, what color's your hat? Gray, cool gray hat, and some other information that we don't really need. And we can play again. Well, let's play the game again and start playing around with that information leaking there. Now, each program will have a different offset for leaking out that security cookie because it depends on the stack size, the arguments on the stack, how big are they, how much are they moved around. So it would take a couple of minutes to find this out. Of course, I've prepared this for you because I don't want to clobber the information with that currently because we already have a lot of ground to cover. Let's have a look at $55P. Well, that is going to be the cookie value in this case, and we can recognize it. That's likely a cookie because it starts with that null byte, little endian, so it starts on the right, thanks to that patent issue that was at the time an issue, and some sort of random looking value, which is going to be the security in there. You are not able to guess what that is. Well, let's give me a gray hat again and play this game again and do exactly the same. Michiel, percentage $55P. And we see exactly the same cookie. Now this makes sense because this program never stopped running. It's a program that runs in a loop. There's a loop on that program to display the menu and to give the users back what they need to see there, the standard menu. The program never stops. So then the cookie remains the same. It only gets generated at the start of the program. Now, there are many C programs out there that run in a loop. Imagine web servers, imagine router software that just continuously listen for connections on a specific web port. What will they do when they receive a connection? Well, oftentimes this kind of programs will fork out a process, and then that process will deal with that client. And in the meantime, we can still listen for new processes. Well, for no connection, sorry. Well, that cookie will be copied out as well because forking just copies out that part of the executable as well, of the program as well. So we'll just have that same cookie. We can have one connection leaking out the cookie. And if then there's also a buffer overflow condition in that program, we can use the leaked out cookie to write it back into the input that we'll give to the program to repair the cookie and overwrite the stack pointer then, the return pointer on the stack. That is usually what happens with a stack-based buffer overflow. So we can see that we're starting to leak out some information from a program that can lead to quite some defeat of security controls that are generally quite strong controls. These security cookies are, if they're used very well, they're very strong. They're difficult to bypass. They're not that easy. Now, we have one more demo here on this, and let's quit this program here again. Clear, that's going to be better. Let's try the user format program. Now, what this is going to do, and I'll display the code first before we actually dive into what it does. In practice, nano user format. Let's have a look at this code. It's relatively simple code. We already know the part where we get information from the user. And what we're asking here is, introduce a domain name, and then we'll generate the login, if you will, the domain login for the admin account. We ask some input from the user. This line solely serves as removing the new line character that fgets introduces, because we want to keep building that string. We add the %s identifier to it to make sure that we can introduce the admin username there that we want to put there. We have double slashes here, by the way, because it's an escapable character, or you need to escape it. If we just put that on a notepad, what actually happens here is we have name equals, say I input michiellemmens.com, name will be michiellemmens.com. It will be like this with the \n. After the formatting happens, sorry, it's not called name, it's named format here. It's for a good reason that it's called format, by the way. It's because it's going to be used as a format string. Then format will be michiellemmens.com without the new line character. And what the strlcat will do is turn that into this %s to then be used in the printf format admin. That's basically what's going on there. That's the sequence of things. So the double slashing here, we can ignore that. That's not a problem for our program. I'll just copy this into the format here so we can see this happening, and we can see it a bit more clearly. Very logical. The admin now, when the program is run, will be copied into this %s position, and we'll have michiellemmens.com \admin. Well, what happens if I'm a bit naughty here and I introduce %p here? A couple of those. Well, you'll have here %p everywhere, and you'll have it here as well. And you, of course, see me coming here. This is going to be here as well. Well, printf is going to do exactly the same that we saw it do earlier. That is, expecting a var2 and a var3 here. Instead of this bracket, it's going to expect that. But that's not there. So we're again printing info from the stack that way. Let's try that out in the program here. For the admin account, what's your domain? %p. And what do we see? We again are receiving some cool output from the stack printed out. So this is an example where the user input, this sort of still seems like it makes sense. The only problem is the format here is coming from the user, and it has not been checked before, and it has not been used in a safe way to print out whatever we need to have printed out here. So this leads again to format string vulnerabilities here. And this one is a bit more difficult to spot than the one where you just have the simple printf, like printf format. That's something you'll spot easily as saying, oh, that's a format string. This one can be a bit more difficult to deduct that this is actually coming from the user as input. Now, we spent some time leaking info from memory. We've seen how that can be dangerous, and what very sensitive info such as stack canaries you can leak out, and with a bit of luck you can reuse. Well, let's take that exact same program here. We've used this program a second ago as well. Let's introduce some other fun in there and try to do writing. Oops, I need to zoom out. Yeah, do some writing with that. And we can see that when a user introduces this, but again, I think this is better shown if I just give you the demo. It's a very simple thing to see if you see it working. Nano-priv-esque, the name gives a bit a hint of what we're going to be working against, or we're working towards in this demo here. But let's try to run the program now and see how we can make it behave. What's your name? We saw an input of %p, %p, P, percentage P, percentage P. Let's see, let's give it another one. See what happens here. Your AD login is, so it'll generate an Active Directory login, a bit like the previous program you see. It's a simple string concatenation thing it does, and prints it out using format strings. We get some output here that looks like a pointer that's going to be around the stack perhaps somewhere. We have a 64 value that's likely a length of something, which is going to be the 100 here, but it's not important to us. We have a pointer to likely perhaps code, something else. What do we have here? 0x 41, 41, 41, 41. Now 41 is the hexadecimal representation of the capital letter A. So what's basically happening here is that we are printing out, we have access to the exact variable that we put in here, the 41s here, the A. Let's try this out by introducing B's. And let's now use the direct parameter access here to print out only the B's. What do we see? 42, the hex representation of B. So this means that we can find our input further down the stack, and perhaps we may be able to use it in combination with that write that we had earlier. I said that we have the percentage n that will write the number of bytes written so far to a pointer that we give it, to an integer pointer that we give it. Well, what is going to happen if we start writing to specific variables there? And if you look at it here, this is a bit of a hint of what we're working at. Value demo is at 0x04A038. That's where the address is. And it has a value of 0A. Now let's look at the meaning of that for a second in this program. We see that there's a demo variable here, which is declared to be 10. It's assigned a value of 10. And we print it out here. And then there's a check. That's a bit of an odd check to have here because it says if that demo value is hexadecimal 20, then do something. Now that's something that's not really normal for a program because there's no operation with the demo variable here. Of course, this is a contrived example, but it's to show you what the power can be of being able to write. What if we could change that demo to 0x20 and then drop into this privilege obtained printing etc shadow? What does that mean? Well, I'm a regular user. If I try to print etc shadow on a Linux system, it says permission denied. I'm not root here. That's not allowed. Why not? Because etc shadow contains the hashed passwords of the users on the system. It's owned by root because of security reasons. Nobody has read access except the root and the shadow group, and nobody can write except root. Well, that's a protected file. And if you leave that lying around on a pen test with access to it for a regular user, if I'm doing a pen test, I'm going to scavenge that file and try to crack those hashes because I may well find the root password then. And then, well, that's privilege escalation by just using a password. So this is a protected file. And this program here apparently serves as backing that up because it says print shadow file here. And that function actually is declared up here, to which I gingerly scrolled past a second ago. It's going to run the bin cat program. It's going to take an argument there. And that argument is going to be an array up here that has the bin cat as the name of the executable first. It's going to cat the etc shadow program. And able to do that, in order to be able to do that, we'll need to set our user ID again to 0 to root, which is the owner of the program, which we will see here. Root owns this program, and it has the sudo bit activated, which means that if we run this program, it's going to run under the context of the owner of the program, being root here. So we're going to get our root privileges back first, and then print out the shadow file. In order to do that, we need to be able to make demo be 20 and not 10. But we saw a way of writing to a specific address with the percentage and identifier. Let's have a look. What was the address again that we need? It's located there. Now we can't just introduce that. If we just introduce that, we say 0x0804A038. It's not going to come out, and I need to give it a 038 percentage $5P. We'll see that it comes out as text. It just identifies that as text. We need to be able to input it as hex. Now we can do that using Python. -c prints -d open quotes prints, and let's try with the A's first so we can show that it actually works. We print out 4 A's. If we pipe that into the privesc, we can input things in the program there. Privesc, we'll see that it recognized that as being A's. If we put 41s in there, hexadecimal, it'll recognize that as A's as well. So we know that we can just input that and it'll recognize it for what it needs to be. The address that we need here, this address, let's put it in. Little endian, Intel, patent issue. So we need to put it in reverse. Whoops. A008. And let's add a string to that. Whoops. Percentage $5p. We know that that is where or we can use X to display it in hexadecimal, just not pointer. That's fine as well. So we can see that the address is in memory correctly. And we see that we have 8, the leading 0 is omitted, 804 A038. So we have our address inputted there. Now we need to start writing there, which is not more complicated. And I'll just minimize this a bit. We don't need it anymore. We know we need to get to 20. That's our golden ticket here to get to that catting of that file. Let's try inputting percentage on the 5th possession, $5. The N, start printing the number of characters printed so far. See how the value of the demo has changed to 10, from A to 10. What happens if we print, for example, we put a 10 there? We get to 13. Let's up that a bit still. 20. Of course, you can calculate this, but this is trivial to do by guessing, so let's just guess it for a second. I'm going to guess here, if I put 23 there, because it's 1D, EF20. I need to add 3 to my 20 I already had, 23, and we get our Etsy shadow file. See, privilege obtained, printing Etsy shadow. That is going to be our if that was being, where is my program here? That's going to be our if, that's going to come out true. Demo equals 20 comes out true. So this way you can write with one simple vulnerability, printf vulnerability, a simple thing to have in many programs that exists. You can start controlling the flow of the program and perhaps redirecting how certain variables are behaving or certain variables are valued. Of course, you may still have other protections there. Address space layout randomization, data execution prevention. The same goes for the buffer overflow, we'll see in a second. This does not nullify those controls, but it still is a big issue if you can start writing around memory. That's not something generally that leads to many good things. By the way, have fun cracking that. The machine will be purged after this. If you want to type it over and crack it, do please feel free. It's not a machine that's internet connected to start with, so it should be great for me to not be attacked then. Now, buffer overflow. In certain occasions, there are functions from printf family that introduce buffer overflow vulnerabilities. In really short, what will happen on the stack is any variables that you declare inside the function that are small variables that don't need much memory and don't need to live beyond the function will be stored on the stack in a local buffer here. Then on your stack at the beginning of the function is the function prologue, which will save the saved frame pointer, which is the base pointer from the function, previous function, will be saved onto the stack, so it can be used to restore the previous function's stack layout when the function is ended. The return pointer will be pushed onto the stack before the call is affected and the control is handed over to the called function. There will first be a push of the return pointer. Now, in normal conditions, this looks something like this. You have local buffers there. You have your saved frame pointer, return pointer, and some arguments on the stack that were passed to the call function. In a buffer overflow condition, in other words, if there are functions that allow you to write to this variable, but that don't check how large this variable is, and they allow you to write more than the variable can contain, then we get a buffer overflow condition in which we can write more than 100 A's here. And we can keep writing until we overwrite the saved frame pointer, and we write a couple of B's to indicate we fully control the return pointer here. If we have stack canaries introduced, which GCC does by default since years and Visual Studio has it since 2003, then there'll be a canary value here. We saw you can leak it out earlier. And again, the stack canary talk from December will go much deeper into that if you're interested in getting more info on that. Now, let's look at a simple program here again. And again, I'll do just a demo. That'll gain us a bit time there and a bit clarity, I think. Let's clear the screen. clear nano, what's this one called? bof.c. What an imaginative name that I gave it. So we read in the user's name. We'll print out some information that's not really important to us here, and then we'll use sprintf. Now you may remember sprintf will print the format string that's generated, and the final result of that will print it out to a buffer, a character buffer in this case. So that's what's going to happen here. It's going to take a domain name that's mentioned here, add the name that the user inputs to it, and then write that to the AD login buffer. Let's give that a go, shall we? I can shrink this one a bit again. Whoops. There we go. Bof. My name is Michiel. It prints out some information that we don't need, and below it just displays what the AD login currently is. Well, let's try to input some A's in there, and let's take 32 because we know that the name variable is 32 characters long. And there's a safe way of taking input, which means that I won't be able to write 50 A's to that anyway and have a buffer overflow in there. I would have that if I use the gets function here that's commented out, but it can be maximum 32 characters. Let's see what that gives. We can print out 32 A's and pipe that into the buff program. Stack smashing detected. That's the stack canary saying, bing, 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 bing. Someone has overwritten me. I am no longer alive. This is unsafe. What has happened? Well, let's recompile this program without the stack canary and have a look in GDB what's happening. gcc bof.c -o bof no canary -f no stack protector. There we are. GDB bof no can. We'll be looking at the ask user function, and the whole problem is going to situate itself here at sprintf. So let's have a look at that and put some breakpoints around that one. Ask user. We'll scroll down until we have the sprintf, which is this one. It's +124. Break star ask user +124. That's before the call. On the call means before the call, and the one just after the call. And let's run the program then and see what happens. This way of inputting that you see me do here, the two forward signs and then the brackets, that's to input into the program the way we did before. So to feed it as input into the program, print A times 32. See that I have my quotes and my brackets lined up correctly. Okay, we're at a breakpoint. 40x $ESP. I'll enlarge it a bit because we're going to need a bit more space to display that on the screen. And we get our 32 A's that are read in, or 32 times 41 that are read in into the name buffer. And we see here that the name buffer is at 03C there. That's what's printed out here, which is handy for the demonstration. 03C means it starts here. That's the first byte then, little endian, remember? Then add login, AD login is 05C. So at 5C, which is here, this is going to be the first byte of the AD login variable. There's still some old data in there, stale data, and we are now at the point of writing into them. We're just before the writes. Let's do that right now and see what's going to happen. Before we do the write though, let's show what the return pointer is. That may be overwritten. What do we have here? 0040068D. That's going to be this value here, 68D. That's going to be the value pushed into the stack as the pointer that should be getting control after the ask user function has completed. Let's see if we can overwrite that. That's at the ATC position. We'll let the writing happen. Look at the ATC position. We see there are 41s in there. Woohoo! We've overwritten the stack pointer. Now, we see that we've overwritten it with 4 characters here, 4 A's. There's a 5th A in there, and there's the null byte after it. So if we want to have precise control over the return pointer there, we'll need to subtract 6 A's from what the writing we've done and change it to 26 and add some B's to show with 42s that we have full control over that pointer. Let's run it. We're at the breakpoints. $ESP. We're still at the same values here, 5C. We'll see that the return pointer is here. Let's continue the program. do it again, and we see we have 42s in there. If I now hit continue, we'll see the program crash saying I cannot execute 42, 42, 42, 42, and that's exactly what it does. We have demonstrated precise control over the return pointer. Now, this is to demonstrate that we have that control. What happened in this program now? Let's have a look at what went wrong here and why this is happening. Well, let me spin up next to this my notepad again. We have here a variable called AD login. And what sprintf is going to do, and it's going to be this line here, I'll mark it so we can keep an eye on that. What that's going to do is attribute a value to that. It's going to write a value to that. It's not really attribute, but for clarity or simplicity reasons, we'll call it attribute to it. It's going to add ad.michiellemmens.com / and then whatever the user inputs as name. Now, if we look at the top, we see that AD login has a maximum size of 36, the size of 36. ad.michiellemmens.com, AD is 3 characters. My name is 14, so that's 17, 18, 19, 20, 21, 22. That's going to be 22 characters long. The name variable has a maximum size we see in the program here of 32. Well, you can see the problem arising there. 32 plus 22 equals 54, and that's more than 36. So that is why we get a buffer overflow condition here, although we are using format string printing. sprintf does not do bounds checking to see if AD login is big enough to fit all that data in there. So that's a vulnerable function there. And by the way, one cool feat I want to show, and I want to look at the clock. We may overrun a little with the questions. My apologies for it, but we will make time for the questions. Don't worry, we want you to get your questions in there. If I compile this program, gcc bov.c-o test, whatever, see how the program does not complain about the fact that I use an unsafe function, sprintf. Now, allow me to change this program just a bit. Let's take my fgets out of there and put a gets in there. Gets is unsafe because it doesn't do bounds checking. That's the exact difference between the two. Let's save this program and compile it again and see how we get screamed at by the compiler saying, warning, 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 gets is dangerous and should not be used. Well, it doesn't have the same scrutiny over sprintf apparently, which is something you could easily miss if you rely on your compiler to tell you if you're using unsafe functions. This may well get unnoticed. Yeah, and by the way, another thing, I was working on an exploit a couple of weeks ago, and this is MS0867. It's an exploit I found on exploit.db, and most of the code I see generally, oftentimes it's exploit code. It has some features in there. MS0867 is an old exploit, but have a look here. sprintf is being used in there, and my presentation was already done, by the way. This didn't inspire me. I already had it set up. sprintf is here. It's going to write to remote name, some string here that has some escape slashes in there. So basically it's saying / IP address / IPC $share, which is the way the MS0867 implementation here will exploit, and then add the server in there, so the server address. And if we look up here, server is 256 bytes wide, remote name as well. So 256 plus something is going to be more than 256, of course. Not throwing a stone here to the programmer. I mean, exploits are not made to be the safest pieces of software in the world. strcpy would not be the safest function in the world to use either. And generally, there's not an issue that this is in there, but it's just funny how you can start noticing these things. Once you develop the eye for being careful with these things, you can start noticing these unsafe functions lying about. Now, we have some time left. Let's talk about protections against this. The easiest one is the last example I gave. I gave the buffer overflow sprintf, this kind of functions. It's very easy. It's like with strcpy and with gets. Don't use the unsafe functions. Use their variants that use bounds checking. This will check the size of the buffer that it's writing to and will not write any more than the size that it is. So that's a good way of protecting against those. That's a very simple one, and that's a general practice for any buffer overflow vulnerabilities that use unsafe functions. You should always use the safe variant, so snprintf instead of sprintf and the other families, or sprintf-s in Visual Studio. There are a couple of variants there. Now, protecting against the standard format string vulnerabilities that we saw, that is more a question of, first and foremost, where are variables coming from? The information you're using there, who put in that information? You as a programmer or the attacker? Bear in mind that you should never trust anything a user puts in. That's something we all learn, that we all know, and we all apply when it comes to cross-site scripting, for example. You should never trust it. Well, the problem arises when you use it as a format string, and the format string being the first variable here, the first thing you give to printf, and fprintf the second thing, but the one that's identified as the format, that should not come from the user. If you do that, then you get the condition that we've shown. You need to print just the output there, and it comes from the user. Use this system, %s or %p if you're writing pointers, or x, whatever, the d, the other identifiers. Use that. That's much safer. That's something, if the user then inputs %p in its variable, it's just going to be interpreted as a string character, as %sign and a p. It's not going to lead to the replacement that a format string is known for. The same with here. If you need to print 2, well, do it this way. It's not the most logical or most intuitive way, if you will, because this is much quicker. This old way just allows you to say, there, you have it, it's working. Here you have to take that step of considering, do I need the string, the float, the integer? It's going to be more natural to just use this one. And if it's an unimportant program, then, well, perhaps why not? But if it's going to go in production somewhere, it can lead to dangerous situations. So basically, yeah, what this line says is don't just rely on compilers telling you, just go over your code and start looking for anything that's printf in there. Any function with printf, fprintf, sprintf, snprintf, go over these and check. This one can create this is a safe function for buffer overflows, but it's not necessarily safe for the format string vulnerabilities. You still need to check if the input is actually the correct input, and it's not coming from a user that can input %p in there. It's not because it's safe against buff that it's also safe against format string vulnerabilities. It's a very important one to look at. Even if they're called safe, they're safe for something, not for everything. Now, if we look at a couple of the programs we saw today, I've taken the time to show you a couple of those that are have safer variants that try to do it a bit better. Sorry, not demo buff, good. A good program. And if we put it next to the bad one, we'll see a difference here being snprintf being used. And we can actually just take this one because I let the old code in there for you. We see that this is the old code sprintf, ad login. Don't do it this way either, by the way, because if ever that size changes and you need to shrink that ad login size to something less, if you leave 36 here, you'll still have a buffer overflow vulnerability that can be potentially exploitable depending on what it looks like. Use the size of option. That's much safer. That's one of the programs we saw today. Nano privesc. Oh, by the way, I can demo why it's good too. Why not? Python-g print a times 50. Why not? Let's go loco. Let's pipe it into bof good. And you'll see that it just prints it out. No, I need to pipe it in there, not just right there. We'll see that it just handles it. It just cuts off after it can no longer read. That's it. It stops there. No drama. Privesc good, the same. We've changed it here to, as suggested on the previous slides, use a %s to print out the message, not just print message. And this way, the user will no longer have control over what's going on in there. Privesc good. Let's pipe something in there. Python-c prints. This wasn't a buffer overflow. Well, we can print it in there as well. %p in there. There, that's fine. Pipe it into privesc good. Well, it just prints out these %ps as string. Perfectly safe. We are no longer having access to anything on the stack that we shouldn't have access to. So, with that, that concludes the talk of today. I'll hand the word to Carol in a second for the questions. Of course, I am not inventing this all by myself. I'm a dwarf standing on the shoulders of giants. The C++ reference is a wonderful reference for information on this, on standard I/O, format string, functions, and vulnerabilities. os.org has a great info piece on the format string attack. And the SANS SEC 760 course treats the format string vulnerability as well, and we'll discuss that. And you'll actually need there to show shellcode execution. It's a great part of the course, and I really loved it back in the days when I took it. So that's a great reference as well. And I'll be handing the floor now to Carol to moderate the questions that you may have.
All right, thanks for that great presentation. I only see one question, so I'll jump in. It says, how can I go about writing exploits?
Sorry, could you repeat the question once more?
Sure. How can I go about writing exploits?
Okay, well, if you start off with these vulnerabilities that we saw, say you start writing to a memory address, you could start replacing addresses of functions in memory, and you can start putting there the address that you want, and perhaps that is the buffer where your input was put. So if I go back to the slide regarding the writing for a second, buffer overflow, where is the writing? It's going to be just before this one. If you start writing then to that address, the address of your buffer, then you could start getting your shellcode executed. So you'll jump to that shellcode then that you've inputted there. You'll be frustrated by address space layout randomization, by data execution prevention, which you'll need to circumvent. But let's start off with that. And if you're interested in general exploit writing, well, the day 4 and 5 of the SEC 660 course are all about exploit writing. Day 3, the Wednesday, we discuss how to find vulnerabilities. Day 4, we start writing exploits on Linux. And day 5, we write exploits all the way from 0 all the way up to buffer overflows that bypass ASLR and data execution prevention, which are quite modern and strong controls. And in specific conditions, they can be bypassed with the right techniques. And you can combine the techniques of that course with the techniques we saw here today, because it's all a matter of you need to get shellcode in memory somewhere, you need to store it somewhere, and you need to be able to run it in a way. So you need to be able to write your shellcode to memory and get it to execute. And we saw today how you can get it to execute by writing to specific areas of memory. And we saw how you can bypass controls using the leaking of stack canaries, for example.
All right, thanks. Another one popped in. It says, so only programs that are compiled with the no stack protector flag are vulnerable?
No, the no stack protector flag is only removed here. I only demonstrated that so we can avoid having the stack canary interfere with the proof that we can control the return pointer. So any program that uses printf in a wrong way, regardless of how it's compiled, can be vulnerable to format string vulnerabilities. When it comes to the stack canaries, well, they are by default included when you compile a program. If you disable that for your exploit development and you try to first gain control of the return pointer, if you want to exploit the final program, you will need to turn them on again. But the stack protector is not linked to the format string vulnerability or to the exploitation of it in and of itself.
All right, well, that's all we have. Thank you so much, Michiel, for your great presentation, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.